came online a little bit later than before, but everybody was waiting, and so right now we have almost everybody except maybe 2 or 3 more students. Hopefully they can come on time. Actually, as you saw, I sent you a few emails last week, and because this semester is our second semester that we have this online, and I can see your face and I can see if you got this stuff or not. And this is my concern, that at the end of the class, I like to make sure that you know how to use this stuff. Otherwise, we waste our time. And unfortunately, we don't have this system here. So, and every semester I have to change a little bit in my method to based on the people that I have in the class. Right now it's even harder because I can't make a direct contact with you to see if you have problem or not. Just I'm asking a question. Do you have any question? And when I see nobody is asking question, so what else can I do? I think, okay, maybe there is no other problem. At this time, I decided to go to the homework. Almost for homework 1 and homework 2, more than 60 to 70 people of the students gave me the answer. For number 3, just barely. I think number 3 was a little unusual. I will go through the solution of that. And number 4, it's easy. Yeah, number 4 is a T section. It's very easy stuff. And still, I didn't get that much feedback from you guys for number 4 as well. I don't know why, and because you're not sending me email. There are some students that they are in contact with me with email. They send me their question, ask me to review that, and I will give them the feedback. What is the problem? So I love this. I like to see you are working on something and you have problem. Even if it's not on time, doesn't matter. Yeah, just do your side and make sure that you did something, and then you know that you have some problem. If you're not solving anything, so you don't know what is the problem. Yeah, and then it's on you because you are not working on your side. Yeah, if you have any question, if some parts is not that clear, okay, I ask you, please talk to me. Even if we need, I will give you an appointment for talk through the Zoom. Yeah, even during the weekend. So I am completely available to make sure I am transferring all this material to you guys. You need this, believe me. So please do your side, and I will do from this side to make sure that we have the best, hopefully. Let's see. Right now, actually, another thing that I'm going to give you next week, the first exam. Please let me know. All the way to the end of this class should be for the first exam. And first exam will cover 2 chapters. Yeah, chapter 4 and chapter 5. Means at the end of today, that's it. These 2 chapters should be for the first exam. And today and tomorrow, I will go through all the solution for the homeworks. I will talk about this stuff to make sure that you have no problem. But believe me, if you didn't solve this, it's another example. And as you saw, example will not solve your problem. You should do it by yourself to find out the problem. Then when I give you the answer, that answer will help you a lot. But if I solve 100 of examples, but you are not solving any by yourself, at the end, you cannot get that much from all these course. Please do harder work. I know you are busy, you have a lot of other stuff, but this is the one that you decided to actually work on. And so please do it. I will help you. I started last week for the shear, and today I'm going to complete this section, and hopefully you can see. Yes, there is one question. What's the question?
When did you say exam 1 will be?
Should be next Tuesday.
Okay.
Yeah. So let me read another chat. Yes, these slides. No. I think. Let me see. Looks like those are not on Beachboard, and I think you need them. Let me. Let me double check because I put them, but if you can't see them, it means that I didn't fall. No, yeah. It's no. Number 5. It's not actually visible from you guys. So let me go and make that visible for you. Okay, let me actually talk about this, and at the same time, it's actually fixing the problem, and you can see the pictures on slides from your side as well. So just please listen carefully. There are some hard equations like this. This one, like any mixed material, for sure, like concrete for rebar, we had 2 parts. One part with concrete, another part for rebar. The same for the shear. Part of the shear will be transferred with the concrete. Look at this, VC, shear that will tolerated by concrete, and we call that nominal. They didn't use VC, yeah? Just remember, VC means nominal shear strength, but by concrete only, without reinforcement, without shear reinforcement. In this case, this is the equation, yeah, and must be less than 3.5 lambda square root of prime C BWD. And we know BW, we know D. And F prime C, we know. Always use PSI in ACI. Remember this. This is very important. Always ACI, we should use PSI. So that's the important thing that always we should know. And VC is the concrete only shear capacity of the beam. Yeah, so on only the concrete. So part of that concrete, the rest should be on rebar. So the total should be concrete and rebar will give us the total shear capacity. So just the slides are on Beachboard now, so you can see them. Please, if you want, just go on Beachboard and you have all these slides. So what's lambda? Lambda is based on the material inside the concrete. If it's all lightweight concrete, if it's a normal weight concrete, yeah, for the material that you have inside the concrete. So sand, lightweight. For us, always we are using in this class normal weight concrete. So lambda is equal 1. What is VU and MU? Those are the shear. As you can see, this is shear diagram. So you should be able to draw the shear diagram and moment diagram. That's the statics and the structural analysis and strength of the material. Yeah. Here we are actually, I'm reviewing quick just to refresh your memory. So VU at any point, VU here is this one. VU here, at this point should be 0. What's the MU? MU at the location that you want to see the VU moment at the same location. So VU MU. And VUD MU less than or equal 1 always. Yeah. And ultimate shear capacity, like the other one, MN, phi MN was MU, the same as this one, phi VC, VUC, ultimate shear strength by concrete. Yeah, this is based on the material. It's not coming from the load. It's from the material. Okay, so this is the what's the phi? Phi is not like moment that we had an equation to find phi. Always 0.75. So it's easier. What's rho? Rho W is AS, total shear, total bending rebar area divided by BW web. If you have I section, web. If you have T section, web. If it's rectangular, BW doesn't matter because web is not just web, it's the rectangular section. So B is equal BW. Find this row and put this in this equation, must be less than this one. In this class, we are not using this equation. Yeah, just I want to make this from now easier for you guys. You are not using this equation because at any location you have to find VC. And for us, we will go to find the maximum shear. So at the maximum shear, you have to find the maximum you have to find the moment. If it's simply supported diagram moment beam, at the shear maximum, you have almost zero moment. But it's not always the case. In frame, you have maximum shear and maximum moment. Yeah. Today in homework section, I will show you and I draw something. I solved them during the midnight. So you can see that I plot them, just draw them something to make that ready for today and tomorrow. So I will show you that section that you have a continuous beam or you have a frame. The shear and moment diagram is not like this, especially the moment diagram is not like that. So it's hard to use. It's not that easy. Yeah, but for sure, with this, you will get more capacity than the simplified method. In simplified method, there are a lot of stuff, a factor of safety that for sure the concrete strength for shear is much higher than that because it's simplified, must be completely safe at any condition, and because of that it has a higher factor of safety than this one. Okay, so this is the equation for when you have high shear and you want to use the better from your material. So it's better to use this equation. It's not that hard. You can see everything is clear. Just plug in all the numbers and find VC. But what is the simplified equation? This is a simplified equation. Q lambda square foot BWD, that's it. It has nothing to do with VU, MU, nothing. Yeah. So we will work with this one. That's the shear nominal shear strength of concrete only. PSI F prime C. Ultimate shear strength of concrete. Phi VC. What's phi? 0.75 always. That's it. So from now, we are using this simple equation for the shear capacity of the concrete. But is that good enough? No. We have to do a lot of other stuff as well. Please follow me step by step, and whenever you have any question, stop me. Yeah, if you have question, let me know. Otherwise, how do I know that you still have problem with the first slide? Yeah, if you have problem with the first slide, raise your hand, text me with the chat, so I will back to that one and I will review. So
I have a question.
Sure.
BUC is the rebar shear capacity?
No. Look at this. VUC. VC is for the concrete, yeah, nominal. And can you remember MN, like MN for a moment? And we had MU, this is VU. VMN was MU, ultimate moment capacity provided by the material. This is ultimate shear capacity provided by concrete.
Okay.
So, yeah, this one is just for concrete. C means concrete. Clear? Okay. Let's go to this one. Per ACI, we should do something, and you can see always your VU, yeah, VU caused by the factored loading. How we can calculate this? You will see in a lot of examples that I am solving here. So VU is coming from the loading. Always must be greater than or even equal. VVC, yeah, VVC, what was that? VC was nominal shear capacity of concrete only. VUC, ultimate shear capacity of concrete only. For sure, this VU, if VU greater than that, it means that the concrete by itself cannot tolerate the load. Yeah, because the shear from the loading is greater than VU ultimate shear capacity by the concrete. It means that the concrete by itself cannot tolerate the shear caused by the loading. So what can we do? Then we have to add stirrups. Look at this. This is the beam. These are the stirrups. These are transferring the shear from here to here. S spacing, stirrup spacing. Yeah. Sometimes you can see it has two legs. Look at this beam. It has one here. What? What's the question? No question? Okay. So look at this other beam. You can see one stirrup. It looks like actually loop. Yeah, it's a rectangular shape. Another one here. Another one behind that. So three at the same location. It looks like they have huge problem with the shear. So they use more legs because the vertical leg will transfer the shear. If you add bigger size, if you use bigger size, or if you add vertical legs at any location. So at over here, it has two legs each one, 2, 4, 6. It has 6 legs. Over here, it has just 2 legs. You can put one here, another just one single at the center. Yeah, one here. Not like loop. Let me show that to you. This is interesting. For you can add if you need more shear reinforcement. You can put something like this around here, yeah, and then tie it over. Sorry about that. It's hard to draw something like this. You can see something like this with actually this side is 90 degree, yeah, 90 degree here, go vertical, and at the other side 135. So it's the best way they can install. So the shape is 90 degree, go vertical, and then go 135. Yeah, something like this. So the rebar will go here, another rebar will go there. It's easy to install. So in this case, we have 1, 2, 3 legs. Just I want to show you the number of legs. Here you can, maybe you can see 1, 2, 3 of these rectangular shaped stirrups. So each stirrup has 2 legs like this. Look at this. This rectangular has 2 legs. 1, 2. Over here, 3 at one location. It means you have 6 legs. Over here, we have 2 legs. If you want, you can add another one between, so you have 3 legs. You can change the size of this, so the area will change. Okay. We call this stirrups. So if you have higher shear, so you have to use more stirrups. You have to use stirrups. In this case, as you can see, when your outside shear is greater than shear capacity by concrete only, then we have to use shear reinforcement, stirrups. So in this case, Vn means nominal shear capacity based on the concrete and stirrup. Look at this, Vc nominal shear capacity of concrete only, VSR nominal shear strength of the stirrup bar only. Add them together means nominal shear strength of the reinforced concrete beam when you have both of them. So VSR shear stirrup nominal shear strength. Okay, how can we calculate VSR? VC, I gave you the equation 2 lambda square root F prime C BWD on the last slide. That's VC. VSR, that's the equation. Yeah. What is AV? AV is equal. Look at this. I wrote everything. It's completely clear. If you read by yourself, you can completely get this stuff. AV is total cross section of the legs. It has two legs, so AV is cross section of this one plus that one. If I add one at the center, so I have 2 plus 1 here. I can change different size. I can use number 3, number 4 at the center. So 2 cross section of number 3 plus 1 cross section on number 4, for example. Yeah. So whatever you want. So AV is total cross section of the legs. So if I use number 4 cross sectional area we know is 0.2. So we have 2 legs, so AV for number 4 is 0.4, 0.2 times 2 legs. If it's number 3, cross-sectional area of number 3 is 0.11. It has 2 legs, means 0.11 times 2 is 0.22. So that's how we can calculate AV. Okay, this is AV. What's FYT? FYT is the yield strength of the stirrup bars. Yeah, yield strength for this one. So far we use Fy for the tension or compression bars. For shear reinforcement for a stirrup, we show that FYT, and most of the time we are using the same 60. But if it's 40, if it's 36, use 36. If it's 60, use 60. Yeah. So these are these two. Then what is D? D the same as before. Depth of the beam. Yeah. D, not DT. Remember, D or DT. So this is D. What is S? S is a spacing between stirrups. Distance between stirrups. So code will help us. We cannot go more than this. This is the maximum S. We cannot go with any number that we want. No. Code give us your maximum spacing. It means that you cannot go bigger than this. But smaller than this, for sure you can. Not bigger than this. Should be minimum of these 4. Okay. The first one, D divided by 2. If your D was 30 inches, so means 15 inch. Then AV, you use number 3. It has 2 legs, for example. 2 legs times 0.11 means 0.22. FYT, for example, 60. You know this. Divided by 0.75. A square root, if you use 4,000 psi, a square root of 4,000. If you have a square or I shape or whatever, that this BW is 20 inches. So times 20. You can calculate this and find a number here. Another one is AVFYT. Remember, this must be PSI. This must be PSI. Whenever you are using equation from ACI, always PSI. 60,000 psi. If it's 40,000 psi. Yeah, in anywhere. So another number from here, or 24 inches. Between these 4, pick the minimum. That minimum is your maximum spacing based on the code. You cannot go more than this. Yeah, I think it's completely clear. Let me answer one chat. So Fy is equal Fyt unless is stated in the problem. Yes, for sure. Look at this. In example on everything, we will give you this. In exam, I will give you this. When you are an engineer, you are designing, you know what kind of Fy you are using. So yeah, so always it's a non property that you know. Okay. So what is can we use whatever we want for the rebar for stirrups? No. AV minimum means total cross-sectional area of the legs has a minimum based on the code. So please write this stuff. All this page is good for you. You need that for in future and for your exam or for PE test. Yeah, you need this. So AV mean.
Can you?
Yes. What's the question?
Can you repeat what does AV mean? That's why I was asking.
AV, look at this. AV is the total cross-section of the legs. So imagine this is number 3. Cross-sectional area of number 3, if you check the table, is 0.11 square inches. So each cross-section is 0.11. If you are using a stirrup like this with 2 legs, so it has 2 legs of 0.22, 0.11. So your AV is 0.11 times 2 is 0.22. If you have 4 legs, 4 times 0.11 for number 3 will give us 0.44. Is that clear?
Yes, sir.
Okay.
Professor, can
Yes.
you show how can you identify how many legs are there again?
Look at this right now. Can you see this is one stirrup? Can you see? This is one stirrup. Is that clear?
Yeah.
So look at this. How many vertical legs does it have? 2.
2.
Yeah. Can you see? 1, 2. Is that clear?
All right.
Okay. So you, as a designer, in future you will make a decision. Imagine I have something like this, a stirrup like this. Yeah, this is a stirrup, not the beam. Yeah. So I have more. Actually, I need more because shear is too much. So I will add another one. Yeah, inside this with the same size. I'm moving them to see you can see better. So I put one here, another inside this. Look at this. I will go another inside this one between those 2. So to increase the number of legs, as you can see, I have in this case I have 1, 2, 3, 4 legs. Like here, 1, 2, 3, 4 legs. So it depends on what capacity do we need for the stirrup. Then we can change the size of the stirrup because the cross section is important. If instead of number 3, if I use number 4 instead of 0.11, I will get 0.2 for cross section. 2 of that will give me 0.4. You can use bigger size or add more legs. It's up to you, or in the exam or problems, we will let you know. So code will ask us you cannot install less than this stirrup. Yeah, so minimum stirrup AV, cross-sectional area of the stirrup, should be maximum of these 2. We know all these stuff. What's S? A spacing. FYT, stirrup F5. BW, web width. FRMC, and everything should be PSI. FYT, PSI. FRMC, PSI. Between these 2, pick the maximum. That's the minimum AV that you must use. Yeah, you can see in example how to find this and how to check this. Okay, so these are the requirements. Then there are some code. All this stuff. If you want to study ACI, you have to go through few pages to find all this and put them together. Yeah. So this one is actually summary of the ACI code. So it's very valuable because you have everything that you want for your design. And just please pay attention. What is VU? VU comes from the loading, ultimate moment capacity. We know that sometimes VU, if I multiply phi times Vn, I will get VU, that's the capacity. But most of the time when we are showing this with the other side, from concrete or something, this side should come from the loading. So if VU coming from the loading is less than or equal phi, this is phi. And for shear is 0.75. What's VC? Nominal shear capacity of the concrete only. Last slide I showed you 2 lambda square root F prime C times BWD. So we know this. If your loading VU comes from the loading is less than half of phi VC divided by 2, then no strobe is needed. Yeah, this is per code. And I put this note for you guys. Please pay attention. This is not good for California. This is for other parts of the universe or United States that we don't have earthquake, but or we don't have a very high risk earthquake zone. But for California, that we have few days ago, we had an earthquake, 4.6 or 7, and it was very long. Duration was long, but that was actually bad when duration is long. So for our case, we are not using this, but I'm showing this an example what does it mean. But for us, we are not using these. Even if it is less than this, for sure use the AV mean. Whenever there is no need for a zero, at least use AV mean. But if the earthquake is not that important, whenever VU is less than half of this, you can use no zero. Yeah, that's it. If your VU is between phi VC and phi VC divided by 2, again, what's phi VC? 2 lambda square root F prime C BWD, phi 0.75. Yeah. If VU coming from loading is between these two, then use AV mean. Look at this. For our earthquake zone, always AV mean must be there, always. But for other cases, if VU is between these two, then for sure we need AV mean. Another case, if phi VSR, look at this, that's the portion that the zero will carry. If this portion, how can I calculate VSR? Look at this, VSR, AV FYT D divided by S. Yeah, okay. You can calculate it. What's phi? 0.75. If phi VSR is less than or equal this equation, you don't need to memorize this stuff. These are code. Yeah, don't just panic that, wow, look at all these equations. No, you can put this in front of yourself and just make sure that you know what does it mean. That's it. And put the right numbers inside each equation. So if your phi VSR is less than or equal 4 times phi square root F prime C, and everything should be based on PSI, phi 0.75. Yeah, so we can calculate this. If phi VSR is less than or equal this, for phi square root BW times D, then a strobe spacing not more than S max. What is S max? Minimum of this. So we have to check all this stuff during our calculations. If we are in any cases, we have to follow the code. Okay. So another time, calculate the phi VSR. VSR is this one, phi 0.75. Calculate this side. If it's less than or equal this, then we can go with S max. Okay. If this phi VSR VSR, look at this, VSR is greater than this one came to this side. 4 phi square root F prime CBWD greater than this, but less than 2 times of this. 8 phi square root F prime CBWD. Yeah, if your phi VSR is between these two, you cannot go more than S max divided by 2. So S max divided by 2 doesn't mean that you must go with S max or no. It cannot be more than S max. So if you go with less than S max, perfect. But you cannot go over S max for this guy. You can go less than S max divided by 2. You can go, but not more than S max divided by 2. So if you calculate S max and you got, for example, 10 inches, so in this case, you can go with 10 inch and less. In this case, you can go with 10 divided by 2, mean 5 inch and less. Not more than S max divided by 2 means you can go with S max divided by 2 and less than that. Yeah, hopefully these are not that hard, but please, I cannot see your face. Yeah, it's your actually responsibility to let me know if you cannot understand this. Don't be shy. I know some of you guys are shy, you're not asking questions. This is not the good time. You want to be a good engineer. I believe on you guys. I believe you are the guy that can be a good engineer. And someday I can say, I know that guy. 10 years ago, he was or she was my student, and right now he's the head of that big company. I love to see that. So help me to help you, yeah, to make sure that you got this correctly. And I'd like to see you in highest level. How? With your hard work and study, and let me know if you have any problem. Otherwise, I can't do anything else. Yeah? Okay, so if your VVSR was greater than 8 times of this, look at this, always we are using just few stuff and playing with those. If you are in this case, then stop. I wrote with red light, yeah, to see stop. Change the beam properties. It means that it's better to go with a higher F prime C, because if you use instead of 3000, 4000, then your VSR should be less than this. It's greater than this when F prime C is 3000. If it's 4000, it should be less. It might be, or go with 5000. So if you are in this case, stop. You cannot use that stroke with that beam. You have to make some changes. One of the changes, change F prime C. Yeah, or maybe change the size of the beam. Change BW if you can. Change D, because if you go with higher D, this side should be bigger. Maybe that side is less than this. So this is a red light. If you are in this case, stop and do some changes, and then check it again. Okay. Any problems so far? For sure, you have a lot of questions. Yeah, because that's new stuff. But these are just, you don't need to just memorize this. There is no need for that. Just understand this stuff, how to use it. Do you know what I mean? That's it. Any question on this? Please raise your hand or talk or chat. Or even if you are shy, you don't want to do this, as soon as we are done with this lecture, at the end, I can have a Zoom with you one by one. Okay, question. What's the question?
On curious as to why there's no AS minimum equations.
So AS for the rebar in tension bar for the bending. As you might remember, we had a rho min and rho max. Can you remember?
Yes.
So rho mean was what was rho mean? AS divided by BWD. Rho mean means AS mean. Rho max was AS max. So we had those.
Okay, I get it. Thank you.
Okay, very good. Good question. I want chat. When I see your question, your chat, it makes me happy. It means that you are coming with me. So for S max, you choose the minimum value calculated from the 4 equation to the right. Yes, that's correct. S max is minimum of these 4. In the example, you will see, but it's better to ask before the example to know this. S max, where do we get 24? Good question. This is one of the requirements. That's from the code. It means that never you should go more than 24 inches. That's it. So in T exam, if they ask you, a designer used 25 inch spacing for S max, is that acceptable or not? You don't need to go and find S max maximum to see if it's acceptable or not. As soon as it's 1 inch greater than this, it's not acceptable. Yeah, because it should be minimum of these 4. See, this is good for P exam as well. Pay attention to everything, can help for your in your future. Okay. Still, if you have question, let me know. I will back to any
And
slide.
then that S max thing is what we use for S and those 2 equations on top for AV min and the VSR.
No. Look at this. That's the maximum S, but it's max. Yeah, you are going with less than this. The final S that you are using, this is that S. It might be S max or less than S max.
But yeah,
whatever yeah, is that clear?
Yeah, the value we find for that
That's
S max
correct.
is what we use for S.
That's correct. You have to calculate this to make sure that your S is not more than that. So you have to go with that S. Yeah, perfect. And also, just look at this limit as well. In this case, you cannot go with S max divided by 2. So if you got 10, you can't go more than 5. You can go 5 and less. Yeah. All together, you have to pay attention to all of these together.
And then once we find Vn, we just go through the checks on the bottom and see what's true or false.
Vn. That's Vn. That's correct. At the end, are you talking about this one?
Yeah. Once you find that and do all that S
that's
stuff,
correct. As soon as
at the bottom stuff,
then that's correct. Find the shear capacity for the hole times V and compare that with VU coming from the loading. Your VU should be less than VVN. Yeah, is that clear? Shear caused by the loading should be less than VVN caused by the material. Okay, let's go and solve example. In this example, to the end of this section, and if you can understand this, you are perfect. If you can't understand this, still you are perfect. As long as you study harder, let me know to help you and do something to make this easy for yourself. Okay, let's see what we have. We have a beam, rectangular beam. Yeah, that's a cross-section rectangular, but it might be T-section, I-shape, whatever. And always you have to work with BW. Forget about the flange width. BW, look at this. For rectangular, BW is B. But for T-section, BW is not equal B. Yeah? So, L20 omega U, total load on this beam, 9.4 kip per foot. Ultimate means factor load. So, find the reaction. How can I find the reaction? Total load, omega, times L divided by 2. L divided by 2 means 10. 10 times this means 94. Look at this. Omega L divided by 2. That's the reaction. Yeah, that's 94. Should we consider this as our VU? No. Can you remember? Last week, I showed you In some places, you should go D from face of the support. For simply support, always go D from face of the support. You as a designer, you can compare your beam with those shapes that I showed you last week to see which one will actually is the same as what the situation you have. If you don't have any of those cases and you don't know, go with RU. Yeah, because RU is more. If you come inside, your shear should be less. If you go to the center of this beam, shear should be 0. If you get closer to the support, shear is maximum. So this is the shear diagram. Look at this. At the center line, the shear is 0. This is the shear diagram. Yeah, shear is 0 at center for this beam. And reaction is VU. Look at this. At support, you have 94 tips. Then in this case, D from face of the support. What is D? We have already the sub D 16 inches, D 22 inches. Okay. D from face of the support. D from face of the support. We should use this as our VU coming from the load. Look at this. I put all the notes. So if you pay attention, I think you can learn just by following these notes on this slide. So D from face of the support, D 22 inches divided by 12 means 1.83 feet. From face of the support, calculate this point. How can we read this VU 76.8? How can we use that? Look at this. This is a simple diagram I just draw for you guys. You can use it a lot, and inside this actually example, you can see how you can use this for different cases and even for other chapters. Just pay attention to this very simple equation from statics. Yeah. So I just cut this from X from the support. Look at this X from this is your RU. Yeah. Okay, RU. Then we have omega U loading on top. That's it. At the X, we have VU. Look at this. All the way to this side, VU should be downward because RU minus a little bit of load will give us difference should go this side. Otherwise, your sigma Fy should not be 0. So if you show this upward, you will get negative number. It means that it should be opposite direction. Don't worry about that. Yeah, but it's better to from a start just make a correct decision, not to do 2 or 3 times or confuse you with negative number. So in this case, I will write up. This is my actually method that I'm always not to make a mistake. I did any load on this diagram upward positive, then put this is equation. Okay, are you upward positive? Omega u downward negative, but omega u is cheap per foot. Ru is cheap, so I can't write just Ru negative omega u. No, what's the total amount of this within this length is omega u times x. Yeah, like statics. So omega u times x, total load, vertical load. Then Vu is downward, opposite side of that, negative, equals 0. So I can rewrite this equation, Vu on other side. So Vu is equal Ru minus omega u times x. Yeah, I know that one of you guys mentioned it's hard to understand if this x is multiply or this is dot. So I have no other choice. Yeah, I have just x and that dot for the multiply. So please just listen to me and try to make that, put some note for yourself and make that clear from your side. This is the only way I can show. So are you here? We know omega u. So that's the Vu you can calculate. So right now, what is the x? We want to see the Vu d from face of the support. It means that your x is equal d. Yeah, X is equal D. That's it. I have this equation. Yes, what's the question?
How did you know to divide D by 12?
Look at it, because this is inches. Yeah,
Oh,
everything.
Sorry, I
Yeah,
see.
everything here is per foot. A span is 10 feet. Look at this. 10 feet, half of the span. A span was 20. Half of that is 10 feet. So everything here is per foot. So I will go. And load here is keep per foot. So everything is per foot. So I will convert D to the foot. Otherwise, you will get 20. That 22 looks like a 22 feet if you use 22 inches. Yeah. Look, just check what actually unit you are using. Then use the same unit. Keep per foot. Keep. You should use feet only. That's it. So, yes.
In this problem, is W equal to 1 inch?
W, what do you mean? Are you
Like-
talking about this
like,
W?
The W for like the width, like how there's like B equals 16 and D equals 22.
Are you talking about BW?
Yeah, that.
BW means width of the web. BW means here. This is your B. If you have, look at this, let me go and show something else. I don't want to see you still have. If those are not straight, just accept those, because I can't draw better than this with this pen. So if you have a beam like this, BW is this one, not that. This is not your BW, this is your B. Web is here. B for web.
Oh, okay.
BW. If you have rectangular section, there is no flange, so your flange is web. Is that correct?
Yeah.
Perfect. Just please, whenever you have question, stop me, ask your question. Then you should learn this stuff better, because you still have something is bothering you and you can't listen to me. Yeah, stop me. I will review that.
Then,
Yes.
for D, how did you know D was going to be the distance away from the support we would use?
Okay, so look at this. You as a designer will make that decision. In exam or test, I will let you know. You know what I mean? So you have, for the case that in real design you have, you can compare your case with those diagrams that you can see in ACI or on the slides on different books, and you can see at what distance. Sometimes you have to go with D divided by 2, sometimes at the face of the support, no D from face of the support. In different cases you have different. Can you remember last week's slides? I showed some different cases, and I told you if you are not sure which one is you should go with the VU at the support, because you need more reinforcement, shear reinforcement. Look at this, your VU will reduce a lot from 94. D from phases support, you have 77 kips almost. Yeah, we lost 17 kips. So if you are not sure 100%, go with the VU. Forget about D from face of the support. Please listen to me. These are from the experience side of the lecture. It's not based on the book. So if you don't know which one, you must check. In the exam, you should follow the exam. You can't say, I don't know, because the exam is something that we went through this and you should know. In P-test, you should know. It's something that it's similar to the ACI. But in real design, when you have nothing close to what you have, go consider VU is equal RU. That's simple. So you need more shear reinforcement. It's more safe. That's it. Okay. So use X equal D. So your VU should be RU minus omega, U means 9.4, times D, you will get 76.8, the number that you can see here. So this diagram is good to see where we are. RU was here, we are not going to use that because we can use D from face of support, this is all. Okay. Then we calculate the shear capacity by concrete only. Yeah. On this diagram, you can see all this together. This is a normal concrete, so lambda equal 1, 2, 1, square root. So I put this 0.5 here. Please just understand, I have to fix this. I should put this on top of this. This is in the power 0.5, yeah, a square root, yeah. Just I have to fix this. I notice right now that I have to fix it. These slides are just for this semester. This is the first semester that I'm showing these slides to the guys. So because of that, sometimes I can see some problems. I'm going to fix them. Just remember, a square root means this 4,000 in the power 0.5, not times 0.5, times BW times D divided by 1,000, convert to kips, because everything is PSI, pound. So the number is correct, yeah, 44.525. I showed this, but this is the nominal. This one is U. Look at this ultimate. How can I convert that to VCU? Phi VC will give us VUC. Concrete only ultimate. So 0.75 times this number. That's, I will show this number here. Look at it. So can we accept just concrete only? No. Look at this. Our shear is here. Concrete can just tolerate this much. So that's a lot. So for sure we need shear reinforcement. But we have to check all the other stuff to see if even shear reinforcement is acceptable or not. Okay. Another thing, we will go with VVC divided by 2. Can you remember we had some limit? If your VVC SR was between those two limits, you should go with VVC divided by 2. Yeah. So with all those stuff, actually, these are the things that we need. Divided by 2, 16.7. We are showing this here. That's it. Yeah. So on this slide, we learned how to calculate shear D from face of the support if it's needed. Then we calculate VVC for the concrete and half of that. And on this diagram, we can understand if they show you in a P exam, a beam shear diagram is this. Can we tolerate this shear with no reinforcement? The answer is no, because VU is higher than the capacity of the concrete. But if this one was between these two, pay attention to all the code. Sometimes they show this VU is between these two. VVC is over there, VU is between these two. Then you have to make decision. You should go with S max divided by 2 or whatever. Yeah, this chart can help us a lot. Okay, let's go. Yes, let me answer one chat. Did we assume a phi? No. Phi is always 0.75 for shear. So for shear, always 0.75. Phi is not number for moment. We have to calculate that. For shear, always 0.75. Okay, let's continue. We are not done yet. We know all those stuff. I just showed that diagram one more time here. Just remember, D from face of support. This is our V. This is VVC. VVC from divided by 2. We got that from the last page. Okay. Then what else can we do? We will go with, we just remember, most of the time, we are going to use number 3 or number 4. Yeah. And one more thing for your exam. In the exam, I'm not going to give you something that you have to just do something and calculate it, and if it's wrong, you have to change it and redo. No, because I know it's taking a long time. So for the exam, that's not a good question. I'm not going to give something like that to you. I'm giving you some question that I give you the cross section with the rebar. I ask you to check if it's good to carry that load or not. So you are checking, you are not designing. Yeah. So in this case, we are designing. So number 3 is good guess, and number 4 after that. More than that for regular beam is too big. It's not good for bending at this corner. Yeah, so we use number 3 stirrups with 2 legs. So this is our assumption. 2 legs, as you can see for rectangular, the easiest part is 2 legs. Okay. So AV, what's AV? It has 2 legs. Each leg 0.11 cross-sectional area or number 3. 2 of that 0.22. That's it. Inch square. This 2 means a square. BW, we know this. Yeah. FYT 60,000. That's wrong. TSI, not KSI. So I have to fix this as well. TSI, not KSI. Yeah. And this is what I have. And S max, what's the S max? So S max is D over 2. D was 22 inches divided by 211. Then S max AVFYT divided by this. What's AV? Over here we calculate that because we pick something and then we calculate S max. If you change to number 4, you will get 0.4. So your S max will increase, will go bigger than this because you use stronger stirrup. So AV 0.22, YT 60 psi, 60,000 psi, 0.75 S square root of 4,000 FRMC 4,000, BW the same as B 16 inches, 17.4. Then calculate this one, the same 16.5 and 24. Minimum of this tree is 11 inches. So your S max should be 11. Doesn't mean that you have to follow 11 inches. No, you cannot pass S max. Yeah, should be less than this. So based on this S max, because I need S. Look at this. I want to calculate AV mean. If I go with S max, what is the minimum requirement for the 2 cross section of number? 2 cross section for the stirrups with 2 legs, AV. Maximum of these 2, 4,000 psi, BW 16 inch, S 11. Yeah, because we decided to go with this. Yeah. Then 60,000, 0.14 square inches. Go with this one, 60,000, 0.15. Maximum between these 2, so 0.15. So, but what we use AV 0.22. So we are good because we use 0.22 square inches. That is greater than 15 square inches, 0.15. So we are good. So if we follow S11, but the same as S max, yeah, and your AV that we pick is very good. It's more than AV mean. So we are good. Okay. So with this AV that we use and with this S11, we are going to find the shear capacity of the shear reinforcement. VSR is nominal, VVSR is ultimate. Okay. The equation, that's the equation for VSR. You can see in the last diagram. V.70, AV 0.22 times FYT 60, D was 22 inches. Yeah, divided by S 11 inches. Everything right now we go with the maximum S. Yeah. So with this one, if you calculate divided by 11, 19.8 actually it should be kips. I think it should be divided by 1,000 because if I use 60,000, it should be pound, but it's kips. So this one divided by 1,000. Just remember, divided by 1,000, you will get 19.8 kips. And what is the required? What is the required? The required is difference between VU and VBC. That's the required. Yeah. So how can I find the required? One more time. Let me see if we calculate that on the other sheet. Yes, we calculate that. your VU was greater than VVC. How we do know? Look at this. VU is here, VVC concrete only is here. So it's greater than that. So I can write your VU caused by the capacity. Yeah, the capacity means Vn times V is equal VVC plus VVSR. Or I can rewrite this based on VVSR is equal VU minus that one. So if I consider VU equal the VU that we have, so the capacity for the stirrup must be 43.4. The difference between these two numbers, look at this number minus this number means that this part must be captured with the stirrup. Based on the equation, this is the equation. Vn is equal Vc plus Vsr. Vn is equal Vc plus Vsr. And Vn is Vu ultimate. And I'm using ultimate coming from the loading, yeah, to at least be able to get this one. Rewrite this equation based on VSR, calculate VSR, 43.4, okay? So I need 43.4 for this one. And VSR is less than, this is a requirement, for phi square root f prime c pwd, f prime c psi. It's less than this, so 66. You can see 43.4 is less than this. So S max can be used. Let me back to the slide that we have this to see what we are using. I calculated VSR and we calculated, and we noticed that VSR is less than this. In this case, stirrup spacing not more than S max, so we can use S max. Yeah, if we were in this case, we should go with S max divided by 2, but we are in this case. So any step that we are taking should be based on the code and Rust. What's the question?
Did we use the check for AV min, the VVC over 2 is less than VU? Did we already do that?
VVC is less than VU.
For this example, did we already check to use AV min?
So look at this. We calculated AV min based on the S max. So do you have any question on this one?
What's the difference between these two? Because they seem to use different steps.
What do you mean different steps? This step and last slide?
Like that last slide didn't have this AV min part. We didn't have to find that. So like, why do we have to find that?
No, look at this. Look at this. Design required shear reinforcement. This is the example. So we have to go all the way to write the shear reinforcement for this beam. Give them the spacing and everything. Yeah, that's the design for shear reinforcement. So we have to start with this, and still we are following these steps for the same example. It's the same example. We are not done yet because we designed the required. We didn't design yet. Yeah, just we calculate the forces and we checked if we can use S max or not. That's it. We didn't find any stirrups and the spacing, required spacing. Just we understand we can use S max, but doesn't mean that S max is good enough for us. Did I give you the answer?
Yeah.
Okay, so let's go after this, and hopefully at the end everything should be much clearer. So based on this one, we calculate the VSR based on AV that we use, and S equal S max. So as you can see, VSR, if we follow S max, we will get 19.8. But we need Look at it, we need 43.4 kips for VVSR. So using SMAX is not good for us. It per code is acceptable that you can use, but doesn't mean that when we can use it, it's good for our situation. We can use it, we use that, and we calculated VVSR. And only with that spacing we can capture 19.8 kips, but we required 43.4 kips. So it's not acceptable. So what can we do? So in this case, we have to find S for required VVSR. So we cannot accept that S for this maximum shear that we have. It's not acceptable. So we should recalculate S for that case that the shear is more. If we were fortunate and you calculate this and the number was 45 kips, so we were done. Use S max for the whole beam. It was very easy. But in this case, no, we can't use this. So what can we do? We still can use number 3 stirrups with 2 legs, but the S equal 11 is not good for us. We need a smaller S. How can we use this? Okay, we can rewrite this equation based on the S. Yeah, rewrite this equation. I think I wrote that on that slide. I'm not sure if we did that or not. Let me see. That's your VVSR. Where is VVSR? Look at this. That's the equation. This equation, VSR, you can multiply it by VVSR. So if you want, you can rewrite this equation based on the S. Yeah, S divided by AV FYT. S equal AV FYD divided by VSR will give us S. Yeah, so you can rewrite this equation based on S. Okay, so we use this part in order to calculate S. Or if you don't want to actually consider that, just in the equation here, put VVSR 43.4 because we want to get 43.4, V.75, AV 0.22, FYT 60,000, D 22 inches divided by S, and S is unknown. Then from everything here is clear except S. I wrote that here, 0.75 times AV times FYT times D divided by VVSR per actually a pound, because here is pound, so times 1,000, 43.4 times 1,000, 43,400. You can calculate that the required S is 5 inches. So with that high number, we cannot go with 11. 11 is acceptable. We check that we can use, but it's not good for this case. We recalculate S based on the required VVSR, and we find that with 5 inch, we can get that number. Yeah, if we go with number 3 at 5 inch. So VVC plus VVSR is equal. Yeah, so this one, VVC plus VVSR is this number, and because of that, at this point we need number 3 at 5 inches. So if you go number 3 at 5 inches, see, you can go all the way, but too much rebar, because as you know, when we get far enough from the support, the shear will reduce a lot. So that's not good idea to use this maximum spacing S, smallest S, for the whole of the beam. So in this case, you can, this part is the design. Yeah, in the real design, you can go with the split this after 7 number at 5 inch. Then we will go with 7 inches. Then after that, we go with maximum S max 11 inches. So that's the case that you can see. For example, If I want to go with number 3 at 11, look at this, number 3 at 5, then number 3 at 11. I want to make sure at what distance I can go with number 3 at 11. Number 3 at 11. What is the VBSR? Look at this, VBSR for number 3 at 11 is 19.8. So 19.8 plus shear capacity of the concrete, VBC, the shear capacity of the concrete, this number, plus stirrup number, VBSR, will give us this point. Look at this, 33.4, VBC, plus VBSR, this number that we calculated with S-max, should be here. So from here to this side, we can go with number 3 at 11. From this point, we should go with number 3 at 5. As you can see in the book, split that to at 7 as well, to use less stirrups. Yeah, it depends on the designer. Some designer, they will go from 5, then stop, then 11, or some designer, they will do this. Yeah, so you as a designer will pick what way you want to go. Okay, so in this case, I want to find the distances. Yeah, okay, I want to see at what distances I should stop number 3 at 5 and start number 3 at 11. Okay, I want to find this x1. The same graph that I showed you over there, you can use this here. See how can we use this graph to find this x1, x2, x3, whatever you want. I wrote all of them here. For example, I want to find for x1. For x1, the same equation, VU here. What is this VU here? This VU, I want to see at this point. Look at this. VU, what's the VU here? 53.2. I hope you can get this. If not, stop me. Ask me and the section in Zoom meeting, whenever you want, I can review this stuff to make sure you got this. 53.2. Okay. This number is your VU. Write the same equation. Yeah. RU minus omega U x negative U, the same equation is equal to 0. So VU is RU negative omega U times x. Yeah. Okay. Then your VU is, we know VU is 53.5, VU1, look at this, because this equation is for everyone. So if I'm using for x1, I'm using VU1, 53.1, yeah? So RU is 94, the same as the first, is your maximum. Omega U 9.4, put this in this equation. You can calculate x1 is 94 minus 53 minus VU divided by omega U, 4.35. As you can see, 4.35. Yeah. So it means that 4.35 from face of the support. If you go, then from this point you can go with number 4 at 11. That's it. Yeah. So at any point you want to check, you can for x2. Just follow the instruction, read at the end, at what end you will get VBC, X2, U is VBC, go on 33.4, find this. What point you will get half of the VBC, X3, go with half of the VBC, you will get 8.2. Let me answer one chat, I saw one chat, let me answer. To find x2 and x3, we have to recalculate VBSR. No, you don't need to calculate VBSR. You just go at this, in order to find x2, go here and see what is your VU at x2 is 33.4. Look at this, 33.4. RU is the same, VU is the same, just with the same equation, find x. What is for x3? Go at the end of this, see what is your VU is 16.7, 16.7, yeah, 8.22. That's it. As you can see, looks like hard, but maybe for the first time is a little looks different. But you can see it's very simple static equation. Okay, let me answer this. How do we know when to use VU 94 tips or VU 70? Okay, if in real for the exam or problems in the book, we let you know, yeah, because you are not the designer. We should give you the whole story. What do we have? In reality, if you know the beam is the same as the beams that I showed you last week, or in the book, or in ACI, then you can follow. If you can go with D from face of the support, from face of the support, you can figure it out by yourself. If it's not that clear, go with V dot D from face of the support. Go with the maximum. So you need more rebar. This is more critical if you go with this and you don't know what your situation is looks like with the compared to the code. In that case, go with the safer side. Otherwise, if you know D from face of the support, go in exam or in the book, we should let you know D from face of the support or from face of the support. If it's from face of the support, this is your VU. Forget about this. You don't need to calculate this VU from the first step. This is your VU. Did I give you the answer?
Sort of. I guess I'm a little confused because in this one example, you've used, so here when we were doing this last part where we were finding X1, X2, X3, we're using that maximum, that 94. But then on the previous slide, at the bottom when we were, so we said like, let's see, when we were calculating phi VSR, we used the 76.8, and I think I missed something. I don't understand.
Now, look at this. Over here, we use RU94 as well. RU is always RU. Yeah, it's not changing. This equation is always based on RU, omega U, X, and VU. That's it. Yeah, all the parameters are the same. And RU is 94 always. Is that clear?
Wait, so... Oh, okay. Wait, I think I got it. Okay.
I think you thought about two different stuff, and because of that, it was confusing. But right now, we are talking about just this sketch to calculate X or VU. It depends on what we want. Over here, we know X. It's D from face of it. So your X is clear. We know X is equal to D. So you can calculate VU. In other X1, X2, and other stuff, we know VU, and then we calculate X. So you can use this for any cases that you want.
Okay, I see what I was confusing. Yeah, thank you.
Okay, perfect. Very good.
And then how did you go about
any question?
Finding the VU1, VU2, VU3s?
So VU1, VU2, VU3 just at the location that we have VVC divided by 2. Can you remember whenever you have shear less than VVC divided by 2 based on the code, there is no need for shear reinforcement. And so because of that, look at this, I put this note, no stirrups required from here to here. Why? Because shear is less than VVC divided by 2. But as I mentioned, this is based not for the earthquake zone. For California, always use the minimum. Go number 3 at 11 inches for the whole section that there is no need. But based on the code, if you are working at some place that the earthquake is not important, from here to here, no stirrups required. From here to here, a min is required. Look at this, I put everything based on the code. So from here to here, AV min is required. So AV min, if you go with S max, you go with number 3 at 11 inches, you have more than AV min. And because of that, number 3 at 11. So just please pay attention to these notes. Yeah, I tried my best to put everything on the slides so it can make it clear. Because as I mentioned in the class, I can talk about this stuff to you. I can show that. But over here, if I miss something, so it's hard for you to read this from the book. So I hope everything is clear, but for sure you need to study more and then get and ask the question. And this is another case that if you, sure.
On the diagram, after 8.2 feet, we don't need steel.
That's correct, but not earthquake zone. Yeah.
Okay.
So look at here. Let look at this. I showed something. Look at this. If VU is less than or equal VBC divided by 2, then no stirrup is required. If VU is between VBC divided by 2 and VBC, AV mean required. I wrote them here. Yeah. Look at this. Less than VBC divided by 2, no mean. Between VBC divided by 2 and VBC, AV mean. Is that clear?
Yes. Yes.
Perfect. Very good.
And then that final S we found, is that going to be the final S for the spacing between?
That's good. This is the final. You need number 3 at 5 inch, this length, yeah, up to this length. Or you can go less than this and 2 more at 7. I didn't do this one, but if you want, you can actually split this to 2 parts. It's not that critical to do this. And then from here, you can go with number 3 at 11, all the way for the rest of the beam, because this is based on the AV mean, yeah, S max, almost AV mean. So this one, we need all the way for the length, and the other side of the beam should be the same as this side.
How did we decide 5 inches spacing?
Now we calculated, look at this, we find S based on required this, based on the equation that we have here for phi SR, we put 43, yeah, so we calculated phi. So let me answer one chat for the chat. A little off topic, sorry, but the test will have material up to this lecture. That's correct. Yes, up to this lecture, the test. Okay, another actually stroke, if you go with actually give you this one to you, just I put that here for you guys. If you have a case like this in real design, follow this instruction for VVSR. Everything is the same, just VVSR will, you have to use this equation, yeah, based on this alpha equal whatever degree that you are going with, 45 degree whatever, yeah. So that's the equation. This is just for your information. This is your homework. One thing that is going to be important as, and I'm going to refresh your memory. You should know this, yeah? Just I'm refreshing your memory, and it's important for the exam as well. Just I'm informing you. Please pay attention to this, okay? Imagine it's not a simply supported beam. It's part of the continuous beam, or it's part of the frame, yeah? So you have negative moment, any moment at any direction. Look at this, I use different directions moment because I want you to learn everything based on one slide. So how can I find the shear diagram? Because you need that shear diagram and that X, and then you can go with different face of the support and other stuff to show on this. So you need this reaction, and you can see they are not equal at this case. It's not simply support. You have moment. So in this case, always make it easy. Yeah, right now I'm teaching you statics, and very simplified statics. I'm going to make that as simple as possible. Okay. In order to find RU1 and RU2, at first I will consider this as a simply supported beam. Look at this, there is no movement. Yeah. Please follow this instruction. This one is equal this plus this plus this. That's it. Okay. Simply support omega u. Omega ul over 2, omega ul over 2. Yeah. So reaction is easy to find. Then I will consider just this moment. Just follow the direction of the moment. Those are important. Otherwise, you will make mistake. When you have this direction moment, this brown actually arrow should be upward. The other side, green, should be downward. Always. So if you have moment at this direction, upward here, downward there. Those two must be equal, different direction. How can I calculate them? This moment divided by length. That's it. Omega u1 divided by L, omega u1 divided by L, opposite direction. And I showed this at opposite direction to actually practice. In this case, as I mentioned, you go that way, should be downward. If this one was that way, it should be downward. Yeah? So this one is going that way. Look at this. This one is pushing this side, so it should be upward. This one is pushing this side, should be upward. Just try to imagine that. Try to feel it. Do you know what I mean? And I believe that you can. You can do it. Just try to feel it, then it should be easier to understand. So this one will go upward. The other one, if in exam I change the direction and you make a wrong decision, you calculate the R by mistake and you will not get any point. Yeah, just follow this instruction. This direction, upward. If I change the direction, should be downward, the other side upward. I put that here. This direction, upward this side, downward that side. So all the brown sides are upward, all the green are downward. Yeah, I use color code. Add them together, that's it. This number plus this number plus this number should be RU1. This number minus this number minus this number, because they are at the different direction, should be RU2. That's it. I hope I gave you the answer. And how can you find X? RU1 divided by omega U. That's the length. Yeah. So, and you can find the maximum moment. That's not the case for this. So this is just for shear diagram. And example unit. Imagine we have 20 feet. Omega u 2 kips, omega u I showed the direction, and over here I changed the direction, yeah, to practice this again. So 40 feet kip that direction, 30 kip this direction. Okay, so split this to 3. 2 kip per foot, 20 feet. 2 times 20 divided by 2. Yeah, that's the equation. You will get 20 kips upward, 20 kips upward. Simply support. This one simple. Then moment at one direction. So this direction 40, upward this side, downward the other side. So moment, foot kip divided by length. Foot kip divided by 20 means 2 kips. Okay, the other side, 2 kips downward. This one, I changed this direction. So upward this direction, downward that direction. M2 divided by length. Yeah, 1.5, 1.5. RU1, I cannot find RU1. 20 plus 2 minus 1.5. 20, 2 minus. RU2, 20 minus 2 plus 1.5. 19.5. So 19.5 here, 20.5 there. Then X is equal this reaction divided by omega. That's the length that you have shear equals 0. And if you need to go deep from face of support, back to the example that I saw. Yeah, as you can see, this is refreshing your memory, but it's very important because simply support beam is not the case. Is most of the time you have this situation with moment at both sides, or maybe there is moment at one side, no moment here. Forget about this side. You have this moment, nothing. Forget about the third side. So this one plus this one minus this. If there is no moment mu2. Is that any question on this one?
Can you repeat again if there was no second moment?
So look at this. Consider mu2 is equal to 0. So you will get 0, 0. It means that there is no. This case is not here. That's it.
Okay.
If there is no moment M1 and M2, you will get 0, 0, 0, 0. You have just simply supported beam. So this case will give you for any case. Simply support, moment at one side, moment at both sides, or you have a beam with no load, just with moment. Just calculate the shear for the beam that has no omega u. So forget about that. Imagine if omega u was 0. So nothing from here. So you have this load, 2 upward, 2 downward. You have this one, 1.5 downward, 1.5 upward. So the shear at this side, RU1, should be 2 minus 1.5, means 0.5 upward. 2 minus 1.5, 0.5 downward. So if you had no omega u on this beam, your reaction should be 0.5, negative 0.5. That's it. Yeah. So this case will cover any case. Simply support with moment at one side, moment both sides, no force uniform load on top, just moment. So it will. This is the case that can cover any situation.
So this covers the situation of having a moment on both sides when you have a load on it.
That's correct. This one will cover everything, with loading and moment, with no loading and moment, with loading with no moment. Yeah. So this one will cover everything. I hope. Yeah.
Professor, is it only for a simple support beam, correct?
No. This one is for continuous beam for the frame because you have moment. Simple support has no moment. This case is for frame. If you have a beam, look at this. If you have a frame, what's the frame? Frame is something like this, that you have, for example, vertical elements, columns, and the horizontal elements, beam. Yeah, I will go with two stories. This is a frame. So in this case, this is not simply support. It has fixed connection. Your moment diagram should be like this. Yeah, this is the moment diagram for this beam and the beam above. So you have moment here, negative moment. You have moment here, you have moment at the middle span. So it's not simply support anymore. You have moment at both sides, like this. Any direction I showed from that side, this side, just follow this instruction for upward or downward load. So this case is for frame or for continuous beam. If you have continuous beam like this one, these are the supports. Yeah. Okay. So in this case, look at this. The moment diagram for this should be like this. Will go to 0 over here. So you have moment here, 0 here. So this moment 0, you have moment there. Or for this mid here, you have moment here, moment there. So you have this case. So it's very rare to have a simply supported beam. It's not always the case. Most of the time you have continuous beam or frame. In that case, you have 0 moment, negative at one side, negative at both sides. So this case will cover everything.
Thank you.
Is that clear for everybody?
Yeah.
Yes.
Okay, perfect. I like this class. You are great. You actually ask a lot of questions with the email and with during the class. Sometimes I have to actually back to different slides. I like that. It's not bothering you when you ask me question. When you ask question, it means that you are listening, and that's good. I like to see I can make contact with you even if I can't see your actually your face. You can see my face, but we are following each other. You can see some pictures. I can see some pictures, but we can get to something the same, and that's the goal that I wanna see. So that's for today, and we are done with this actually 2 chapters for exam 1. And one question. Yes, what's the question?
It's actually about the test. I was just wondering what kind of format it's going to be in and how many questions and how long we have to take it.
Okay, that's actually a good question. I'm giving you guys, please just listen to me. Don't panic. I'm not going to give you a problem long and you have to make decision how many rebar you should pick, and then it's not acceptable, then you have to pick. No, I know that it will take time, especially for students that just started. Yeah, I'm not going to ask something that is unusual. Yeah, so I will give you something, a beam, and with the rebar and everything clear, and then I will ask you if this beam can carry this load. That's it. So you have to check. So the exam is you have to check something. You have to find something based on the data that I'm giving you. I'm not asking you to calculate. Maybe I ask you calculate AS, but I don't ask you to go and repeat if it's not acceptable. No, just one time. Yeah, or I will give you the river and I will ask you if it's acceptable or not. So most of the time, the question are just checking the beam to be able to carry the shear force or the bending moment. That easy. Believe me, it's easy if you study. For those that they didn't work on the homework, it makes it harder for them. But still, it's not impossible. You still have time. You can study. That's your first exam. And I'm giving you few small problems. And each one, I will give you time, 10 minutes, 15 minutes, something. And I will ask you, as soon as I'm done, take picture and send it to me. Yeah. So the time is very important. I will, on my other computer, I will check how many actually answer I got from you guys. So that's the case that I can check. So as soon as you are done, then as soon as the time is over, I will give you 1 minute more extra to just take picture and send that to me, and then I will give you the second problem. And for those that they send me with delay, I'm not going to accept that because it's not fair. Yeah, if the time is closed, so it must be fair for everybody. So you have time for the first question, then 1 minute to send that to me. Then I will give you the second one, 1 minute to send it. And third, if I'm working on it to give you 3 or 4 questions. So it should be very small and easy if you know these stuff, just how to use them. Yeah, don't worry about the hard problems that for sure you have no time to work on them. Any other question?
For the homework review that you're going to do this week, are you doing it for both labs this week?
For both lab this week, sure. Yes, I'm doing this, and I've spent a lot of time, just as I mentioned, on midnight, because during the daytime I have no time. So I spent that night and I wrote by my handwriting. I took picture. I try not to make any mistake. Hopefully by multiply, divided. So I tried my best, right? And I think there is no mistake on that one. And I took picture, and I'm going to actually show them during this lab hours to you, and you can see the process. Yeah, you can see it's exactly the same as examples. Just problem 423 is one of the hardest for this class. 423 for those that they solve this. Just few students solve that, and the rest I'm not sure if they went through and they saw that's hard or they can't do that. If that's the case, I'm still more comfortable to hear something like that. But if you never went through the homework, that's not good. It's not something that I actually I like to see from the student, that must have respect to the class. When I'm doing this stuff, because I have respect to you guys. I believe on you guys. I know you might be one of the biggest engineer in future. So when I think something like that, it's not fair not to give you enough information. Yeah. So these are stuff that I want to actually let you know. So any other question?
We're going to be sending you the test answers through email, correct? Not Beachboard?
That's correct. That's correct. You will send that by email to me as soon as you are done. I will give you 1 minute left, and then please send that over. So take picture from your handwriting from that, and then send that to me. And the time that I'm receiving, that is the time that I'm checking, because I put note on my exam what time it started, when it should be done, plus 1 minute. Then I have to receive all the answers. Then I will give you the second one. Yeah, so you have no time. If you spend more time for the first one, you will lose for the second time. So then it's, and the questions are that easy that time most of the students can send that even earlier than the time that I gave you guys. Believe me. Yeah, don't panic. Just read this stuff. Solve all the examples by yourself. Believe me. Solve all the examples by yourself. You to give you the solution for the homework. I accept that. I am doing this, but it's not helping you that much. Examples. Other question? Okay, so actually just I don't know if number, please let me know if student number 16 and number 18, 16 and 18, are they here in this class right now? If you are, please by chat let me know. Number 16 and number 18, because I didn't check you in my class today. Let me see. I'm here, number 18. Thank you. Thank you. And so number 16. Is number 16 here? And another one is number 11. Please let me know. I think number 11 decided not to continue and drop this course. So, but I still saw you in this class. Are you going to continue in this class, or please let me know your situation? Number 11. Okay, so I'm done. Please, you can go. And for those that they have lab, please stay. I will continue reviewing the homework. Thank you for being in this class. Thank you.